maybe later.
And could you switch off the light?
Sure.
Let's see. There you go. Just first try? Wow.
Yeah.
Good.
Okay.
Hello, everyone. We are very happy to have Pedro Bittar giving us a talk today. He is a PhD student in the University of Sao Paulo, but he's visiting us here at Chicago for this quarter. And today he'll tell us about matter asymmetries in twin worlds. Take it up.
Okay. Yeah. First thing, I'd like to thank Harushi for organizing this nice seminar, and also Carlos for inviting me. So I chose this title, Matter Asymmetry in the Twin Worlds. You'll see quite soon. But I'd like to start. Okay. I'd like to start by remembering some old tradition in theory-driven approach to model building nature. It is around 100 years old that we started doing this. And the thing is that for some theoretical reason, we propose a new particle to exist. So Dirac started that with the positron, for example. And then years later, experimentalists went on and found these particles in some experiment. So I have several examples of that. And this is one of the reasons why particle physics was very successful in the last century. Up until the Higgs. So we all know that the Higgs was discovered in 2012, and it closes this era of prediction and discoveries in experiments. So this gives us a nice feedback loop where we start with some puzzle about nature. Could be, for example, the CP decays of kaons, or could be the origin of masses of gauge bosons and fermions in the standard model. We come up with some sort of argument. It could be either from symmetry, consistency of the internal theory, naturalness, some new dynamics that we need to explain something. And then this points out to some way to do some experiment and discover the proposed versions. So this is why this program has been very successful in the past. Of course, today there is no shortage of puzzles. I decided to talk with you about mainly 3 of those in this talk. The first one is the electric scale stability. Why is the Higgs so light compared to what we would expect it to be if we included another new physics at the UV? The second one is dark matter. We know that dark matter exists. There is, for sure, we needed to have a consistent picture of the cosmological universe. So we want to know what can be formed. And the third one is the origin of the particle and anti-particle asymmetry that we observed also in cosmology, in the real world. And this requires a mechanism for the baryogenesis, the origin of baryons. There are also other puzzles like gauge unification, neutrino masses, and so on and so forth. But I'll focus on this. Of course, also there is no shortage of some arguments and ideas to solve these problems. And for example, for the electric stability or the hierarchy problem, the most famous of them is supersymmetry. Supersymmetry postulates that there are new particles that will cancel this large contributions to the Higgs mass. For dark matter, we have several candidates. One of the most famous is called the WIMP, weakly interactive massive particles. And because of the so-called WIMP miracle, it gives us exactly the right abundance we would need to observe in the universe. For baryogenesis, there are several models. One of the most famous also is this high-scale leptogenesis, in which you generate some lepton asymmetry at very high energies, and this gets transferred to baryon symmetry. And this also
Bias-Valerons.
Bias-Valerons, yeah. Yeah. Similar things for this gauge unification, neutrino masses. All these problems somehow in the past correlated with each other, and we could form some consistent picture of what would happen at very high energies in the past. Of course, we know that there weren't any new discoveries after the Higgs. So for the electric stability case, for example, with supersymmetry, we would predict some colored new particles to appear right as we turn on the LHC. And that so far it didn't happen yet. So this is being challenged by the LHC data. For weakly interactive massive particles, we also did lots of experiments. For example, direct detection of dark matter, indirect detection, and also looking for them in colliders. So far, nothing. And for high scale heterogeneous, for example, it's very hard to test explicitly because these things is so live at so high energies that we couldn't come up with experiments to test them yet. And this continues. Gauge unification, for example, is challenged by not seeing proton decay and so on. So the first thing I would like to argue is that, of course, a discovery is not some new particle. We should know that, but because of this long track history of getting discovering new particles, we started to think that way. But also, no results should be important, and they should update in a way our credences of these models. So it's nice to come up with new ideas that somehow correlate all these problems together. So this is what I'm going to talk about today. So the first one is related to the electrics hierarchy, is neutral naturalness. The second one will be asymmetric dark matter, and the third one will be having lower scale baryogenesis. And in this seminar, we'll connect these ideas in the context of the twin Higgs model, which I'll present to you soon. So part one will be me discussing how does the twin Higgs solves the naturalness problem. In part two, I will say how you can get asymmetric dark matter in this model. And then in part three, I will comment a couple of work that I'm doing now with neutral baryogenesis and long-lived particles. This is all based on some work that I'm doing with Gustavo, Burtman, Larissa Kiriliuk in Brazil. And also now Seth joined me with a new program. Okay, so let's start. Twin Higgs and the neutral naturalness. So the electric scale stability, we all know that in the standard model, there is no symmetry that protects the Higgs mass. So once you include these radiative corrections, you get this quadratic dependence on the high cutoff of the theory. And this is why we expect the Higgs to be heavy. If we want this relative dependence with respect to the mass to be of order 1, then you point out to this mass scale at the TeV energy range. So this is why the TeV is a nice scale for the LHC to probe, because we expect something to happen. Using the old strategy, we postulate that there are some new states and that there is some new symmetry that should induce more contributions to the Higgs mass. And this new symmetry makes it so that these large contributions cancel. So this is what supersymmetry does. Of course, supersymmetry predicts colored particles, which is something that we would expect to see at the LHC at some point. So I'll focus on this talk on having some discrete symmetry protecting this, making this cancellation happen. And this will induce neutral partners. And this is why this is called neutral naturalness. So one example of this is the twin Higgs, which can be generalized to something that's called orbifold Higgs, that maybe I comment a little bit on this. And the original twin Higgs model is fairly simple. So you have a new global symmetry, SU4 times U1, and this global symmetry is broken down to the SU3 times U1, such that you put the Higgs as a non-Lugolston, one of 4 degrees of freedom of this breaking out the Higgs, and the remaining ones are the second Higgs. So we will call it a twin Higgs. Out of this unbroken group, we gauge the standard model part. So this is the standard model, and also we gauge another SU2 symmetry. So this will be another SU2 which will be related to this twin sector of the theory. So far we have the Higgs, then we have the twin Higgs, this one, and then we also have the W's and the Z's, and then we have the twin W's and twin Z's associated with the gauging of the other SU2. And since we want to cancel also for example, the top contribution to the Higgs mass, we need to include fermions and twin fermions. So this will lead us to some model building, but in principle we have this structure. You have the standard model sector, and it gets mirrored into a new sector that is like the standard model. Okay, so when you do this gauging of this global group, and when you include the Yukawa terms, of course, you generate some radiative potential to the Higgs. So, for example, here is the contributions of the W's and the twin W's, and they have the dependence on the coupling of the sector A, the cutoff, and the Higgs and the Higgs W. The same thing for the Higgs B. So the trick now is to impose some discrete symmetry that will relate these two sectors. So it transforms Higgs A to the Higgs B. And to do that, we need the coupling GA, the gauge coupling GA to be equal to the coupling of GB. And then once you do that, you can rewrite these contributions as an SU4 invariant term. So this means that accidentally you restore the initial symmetry, the initial global symmetry, and then you won't expect it to induce a large contribution to the Higgs. So we need to start thinking about what is the quality of the C2 symmetry, in the sense that if it's how it's broken, if it's broken hardly or softly, and this can be done in several ways. So in the fraternal Higgs case, we just copy the most immediate states that are necessary to solve the hierarchy problem. That is the third generation, the top quark. So we only copy the third generation of fermions. And by doing that, you introduce some hard C2 breaking in this C2 symmetry, because you are explicitly not including the couplings of the second and the first generation. So the UV cannot be exactly Z2 symmetric anymore. In the mirror twin Higgs, which is what I'm going to focus on this talk, you copy everything. You copy all also the first and the second generations. And in this case, it's possible to have some Z2 symmetric UV theory. And this will be nice for reasons that I'm going to say later. Either way, either the fraternal or the mirror twin Higgs, this Z2 must be broken softly in the infrared. That's because we have measurements of the Higgs couplings, the first, and also the invisible Higgs decays. And if this Z2 were exact, if the two sectors lived at the same scale, then we would expect the Higgs to decay half of the time to invisible states, which we know that's not possible. So since we have a bound on the invisible Higgs width, then we can set this bound f over v to be larger than 3. So the twin sector will be a little bit heavier than the standard model sector. Of course, having a soft C2 breaking, for example, you can put some mass term that will make the twin Higgs heavier. This doesn't affect the hierarchy problem. While if you have some hard Z2 breaking, this will reintroduce the hierarchy problem, because if you change the Yukawa couplings, for example, you change the fine matching cancellation of the two contributions. Okay, now that I revealed the twin Higgs, I would like to talk about how asymmetric dark matter appears in it. We start by remembering the observed fact that the dark matter abundance is more or less 5 times the baryon abundance. And we'll look at this and we'll apply the same logic in the twin sector and look for the matter candidates in the twin sector. And we see that the twin baryons would fit nicely as a dark matter candidate, mainly because they already give some similar abundance with visible and dark matter. So because of this, asymmetric dark matter fits really nicely in the mirror twin Higgs. You already have some mirror neutrons, mirror protons, and these are nice candidates given some baryogenesis.
Everything in the mirror sector is invisible for us, basically.
Yes, everything is invisible. We have some portals, the Higgs portal, for example, but other than that, it's invisible. So in the mirror sector, we have mirror QCD, and the mirror QCD will have mirror protons and neutrons, and these are the dark matter candidates, mainly because they give some similar abundance.
Mirror atoms and things like that.
So that's some issue that we have to do.
Mirror Pedros.
No, actually, we can't have that.
We cannot have mirror Pedros.
How do you see that, like, it's okay to have 5 times as, like, I'm assuming all of the dark matter is mirror baryons?
Yeah.
But then why is there this asymmetry between the mirror baryons and our baryon?
Yeah, that will be an important theme here too, because we get a similar abundance, but we have to explain now the factor of 5. So this is what this slide is telling you. So in the usual, when you think about thermoradic dark matter, for example, WIMPs, you think that the abundance is set by some freeze-out process, right? So you are in the following the equilibrium distribution, and at some point the expansion rate of the universe becomes large enough that you decouple, and then you freeze out at some relative density. But this induces another puzzle. Mainly, why is the dark matter abundance so close to 5 times the baryon one, when it could have been orders of magnitude different if you have some different coupling? So if you change a little bit the coupling, you have orders of magnitude difference in the final abundance. Whereas in the asymmetric, in this asymmetric twin dark matter case, the same baryogenesis mechanism will set the abundance in the visible and in the dark sector. And so they are related automatically. We assume some out of equilibrium decay for this work. So we have some new particle, it decays to baryon number and generates the baryon symmetry. You copy this to the twin sector, so you have some twin particle decaying to twin baryon number, and also generates this final twin baryon number. And then we have to explain just a factor of 5, not a factor of orders of magnitude. However, in the twin Higgs, this can be a little bit tricky. So we want to compute what is the mass of the dark matter candidates, and this can be done by comparing the QCD scales of the twin and the visible sector. And by looking at threshold contributions for the quarks, you can find this relation. So it goes as F over V to the 2 nines. And we see that this won't be enough to get the factor of 5 that it's essential. So I said to you that the minimum value for F is close to 3, F over V is close to 3. And this induces a twin QCD coupling that is 1.3 times the R lambda QCD. And so dark, if we allow F over V to go as, say, all the way up to 10, then we can get this very narrow window for dark matter. So it's very hard to get twin dark matter much heavier than this. And if you want to get it heavier, then you have to induce a lot of fine-tuning in theory, which is something that we don't want. So if you look at this relation, so I can rewrite the abundances as a number density times some mass. And if this thing is 1, then you would predict that the dark matter should be 5 times the proton mass. But actually depends on the relationship of the number densities. So this is what was done before in the literature. So these papers, they looked, yes.
Can you get the other? Why the QCD scale is related with V and F?
So at first sight, this might not be clear, but to find this relationship, you have to remember that as you run the QCD couplings, you once you reach the quark masses, you get some threshold contributions from the quark masses. And then this quark mass, these threshold contributions will have a dependence on V if you are in the visible sector, or F if you are in the twin sector. And then you can compute this relationship. You can look at how it's done in our paper.
And your dark matter candidate is the proton of the mirror sector.
Yeah. In the end, we want to look what is the dark matter candidate is something that we will look here. But in principle, we want it to be the nucleus. Okay, so one way to deal with this is to say that there is hard Z2 breaking in the QCD couplings. So if you allow to have some hard Z2 breaking, then you have some extra dependence on these alpha QCDs, and you can change this in the UV so that you can get a dark matter to be 5 times the proton mass. But this, of course, this requires hard Z2 breaking. So this is not something that we want to do. To not spoil the hard proton. In our case, we'll try to find some reason for the number densities being different, and then we can find this window to be satisfied for dark matter. So let me do this in an explicit model. So we'll be dealing with a low temperature baryogenesis model, where the baryon symmetry is generated directly through the out of equilibrium decays of some new particle. And if you do this, you have to be careful with exactly sphalerons. Because you have if you are above the sphalerons temperature where they are active, this is around 100 GeV, then you wash out any baryon asymmetry that you generate. You can only have B minus L, and we are only generating baryon. So you can generate it below it, but if once you reach BBN, you also can't change anything because you have to keep the proton to neutral ratio, for example, and there are several bounds from these efforts. So in the minimal model, we have two flavors of these N guys, and we also have one colored particle, and we add these interactions. So N is new singlet. We will interact with U and X, and you have also a DDX interaction. This is very useful because it doesn't induce proton decay, and it's a model that people have used before because of that. And
So it's like a leptoquark. X?
yes, this is like an leptoquark.
Okay, good.
Actually, it's not a leptoquark because there isn't a lepto part. It only couples to quarks. But it's one of the.
I thought that N is. What is N?
N is a fermion singlet.
We can call it neutrino. Or we can...
Yes,
Okay.
so you could.
So it's a lepto.
Yes, and X is a scalar leptoquark.
Very good.
Okay.
So, but N doesn't couple to the lepton sector. Doesn't act like a.
That's a model building choice.
It's a model
And
building.
this is something that's interesting. I will comment a little bit in
Okay,
here.
because
This
code-
happens,
Continue.
this happens in the standard model in our sector as well.
Yes.
But with the Higgs and
No.
Yeah.
Because U is colored. No?
yeah, that's why there's nothing like that in the standard model. Oh no, what you meant in the standard? Yeah.
In our sector.
Sorry. I thought that you were really meaning standard model.
This is
This, I don't know what I mean, but this will be.
No, what you-
park.
What you meant is standard model sector.
Yeah.
sector.
the visible sector. So this is something that we add to the visible sector to generate the baryon symmetry
Right.
in our sector and also in the twin. So the way I'm sorry, do you want to ask something?
No, I thought. Sorry, X is the lepto part,
Yes, X is the lepto.
but then you also, X bar is not, no. X bar is
No, X bar is the conjugate. Sorry, my notation.
but
It's the same particle.
X bar is okay. But that lambda prime breaks lepton number,
Lambda prime.
breaks lepton number, right?
Why?
Because does D carries lepton number?
No, right?
So X carries lepton number,
Yes, X carries baryon number,
not lepton number.
not lepton number.
Then lambda breaks lepton number.
Then these two together break lambda. So X has a baryon number, and this decays. So the decay we will generate baryon number is this one, and one going to U and X, and this final state has baryon number 1. Because
And you don't care about the n number
no,
constant.
no, yeah, and the thing.
And it's a Majorana fermion for
Yeah.
you.
Okay, so this is how we generate the final state with baryon number. Then the other Sakharov conditions have the CPA violation, and this is done by some interference between the tree level and the loop diagram here. So in this case, N1 goes through this loop that has to be on shell in order to have an imaginary part, then mixes with N2, and then decays through UX. And you also have the other part. So this is how you generate this ACP symmetry. Now we need to assume that N1 was efficiently produced in the early universe, either thermally or non-thermally. This is not really a big issue. And then we can calculate the baryon symmetry from the N1 yield, the number density divided by the entropy, and the CPA symmetry factor, which is CPA symmetry is given by this right? The yield times the CPA. And if you plug in the values, you find out that you have some dependence on the coupling, and also that some dependence on the phase between these and these diagrams.
What is the 2 there?
Two. Sorry, this is 1. The coupling associated with. Wait, no, this is 2. This is the coupling associated with and 2 with U and X.
I see, because there is no. But it's not the relative phase here. So lambda U1 doesn't appear.
No, because it cancels out because you are dividing by the total width.
Oh, very
So lambda 1 cancels.
by the main contribution.
Yeah, and lambda 2 remains here, and then you have some phase of all of these things.
Fine.
So okay, remember this phase, it will be important later. Now we go to the dark matter part. So it's the same story. You have the same Lagrangian with the Z2 symmetry. Oh, sorry, I forgot to put the tildes here, but this is meant to be all twin sector. So you have the same processes generating the twin baryon symmetry, and you have exactly the same expression for the baryon symmetry. Yeah, that's the previous slide. Now we can remember something that is, I call it here a soft phase breaking, because DCP violating phase is not fixed in the twin sector. So if you think about the standard model and the twin sector, you can make independent rotations in, for example, the quark matrices, and not necessarily these two are related. And if you allow the standard model and the twin sector to have different phases, then you can get around with this problem.
Why are they not related by Z2?
In principle, because it's not observable, but we argue that this can be some sort of infrared effect. So as you relax the theory,
The dark one is predicted by dark string theory. Our one is predicted by our string theory, and those two string theories are Z2 related. If I have a fundamental Z2 symmetries.
yeah, this is the UV, but I'm arguing here that this phase difference can happen in the IR. So as you relax both fields, they can get independently different field rotations. So that you can get so that you can have in the end different phases in this respect. I don't have an explicit model. That's the problem. To do that
Without the breaking Z2.
without hardly breaking the two in the UV.
Yeah.
So for doing that, I think I should do something like have some flavor model where the CKM phases are different, and I didn't want to do that. I think the argument here is just that as you go to the infrared, you can have independent rotations of the two sectors, and if you are not convinced by that, I think this is the best argument. A phase and some coupling doesn't reintroduce the hierarchy problem in any way.
Okay, well, I want to understand one thing. So then, what asymmetry are you computing here? So the fermion asymmetry, but the leptoquark eventually will decay, right? What's going on with that?
I'm computing the twin baryon symmetry. So X already has baryon number, and it will decay to baryon number in the end.
Right.
So that's how you generate baryon symmetry. I'm not using any lepton asymmetry.
No, I understand. So that was not my question. So,
Oh, sorry.
so then you generate an asymmetry in U and in X.
Yeah.
Yeah.
Uh-huh.
That are
In this final state has baryon number 1. So that's how you generate some baryon symmetry.
Okay.
And later X decays to DD.
so X has baryon number 2/3.
Yes.
Yeah, and U 1/3.
Yeah,
I see.
exactly.
That is the idea. Or minus 2/3. I don't know what.
Yeah. And the way we get around this 5 factor is by saying that there can be some mechanism that makes the phase different in the two sectors. So if you allow for that, then you can get away with it.
So this is decay out of equilibrium.
Yeah.
N.
And N is decaying out of equilibrium.
So there's some coupling that's small.
Yeah.
Okay.
Does it matter at all how fast X decay?
I don't think so. X will decay because X is heavy.
Yeah,
Then it decays very early on in the thermal history, and then you produce UDT.
but doesn't matter. There is no bound on that coupling.
No, there's no bound.
Okay.
Yeah. Okay, so we use this phase misalignment argument. And once we allow for that, we can see what phases work, how misaligned they have to be. So in this plot, I'm showing the phase in the twin sector, and this is the phase in the standard model. And if you live in these blue curves, here's a zoom. If you live in the blue curves, you satisfy the requirement of this being 5. So I'm plotting this curve here, and for different hierarchies of FOVR, I get different curves of these different bands of.
Sorry, why is the phase needs to be misaligned for you?
Because if you have a dark matter that is 1.3 GeV more or less, then you have to satisfy the.
You need a little bit more.
You need a little bit more. So if the phases are misaligned, then you can say that, oh, this leads to a factor of 5. If you are in the yellow region, you also still can get a factor of 5, but this is large tuning, so we don't want that. Okay, now that we have a way of having a right abundance, we have to worry about twin Higgs cosmology. And in the original twin Higgs model, this is very problematic, mainly because of dark radiation bounds. So if you copy everything and you don't worry about that, you have too many light degrees of freedom. So you have twin neutrinos and twin photons if they are gauged. And this leads to a very large delta effect, which is constrained by BBN and CMP data. And of course, several solutions for this were proposed early on in the twin Higgs history. You could have some sort of asymmetric reheating, where some particle decays more to the standard model than to the twin sector, and this heats up the standard model, and it makes this bound less strict. And this has been done by Chaco, Craig, and I heard that David Curtin is working on a baryogenesis model that's also asymmetrically reheating.
You have asymmetric reheating, you also breaks the relation that they.
Yeah. So I don't know how they will do that, but they said that they are putting the paper like in a few weeks, maybe.
You have to give up something.
Yeah.
Probably give up on different things.
Yeah. But in our case, we just choose the easiest solution, which is to give some large mass to the twin neutrinos. And this can be done by a soft breaking term. You just regulate the seesaw in the twin sector to have heavier neutrinos so that they don't contribute to delta effective.
But the twin photon is still there.
The twin photon in this model is there, yeah. But you can get away with it. It's like marginally in tension with the constraints, but still allowed for a single twin sector. And this also has been done by several people.
What is the temperature of the twin CMB? Is there a twin CMB? Yeah.
Twin CMB
Has to be.
Yeah.
Well, depends on, are you going to Higgs the dark photon?
No.
Yeah.
But I'm getting there. Yes.
So if twin Pedro tries to get the radio signal,
I think he needs you need the stable to be the dark neutron.
Yeah. We need that. So I'm going to that.
And then you don't have a recombination.
Yes. This is what's not usually. So let's recapture what happens in the visible in the twin sector. The baryogens in the standard model proceeds this way. You have these decays generating baryon number with no lepton number. That's okay. We don't observe any lepton asymmetry. It could be an neutrinos. Then you have the QCD phase transition and produce protons, neutrons. These are stable approximately for the neutron. And all the others decay. The pions, the other hadrons decay. And you go through BBN and the usual cosmological history. And in the twin sector, we have the same decay going to twin baryon number, no twin lepton number. But once you reach the QCD phase transition, because the neutrinos are heavy, now the pions are also stable. So you have these relics. The pions will continue to annihilate through pi scattering. And if this annihilates to pi zero, the pi zero will go to photons. And this will happen until their abundance is negligible. So in the end, the abundance of pions goes down, and you're only left with neutrons.
You want to make neutrino heavy for dark radiation.
Yes. And once you do that, you also get a pion as a relic candidate, but this annihilates.
Does it need to be heavier than the pion?
Yes. It has to be heavier than the pion in order for the pion. Well, usually, okay. There's some.
Because the dark radiation is relativistic, and.
But if the twin neutrinos are very heavy, like GeV, the weak scale, then the pions are stable and they continue to annihilate until their relic abundance is negligible.
And the protons and neutrons are stable.
And they are stable, yeah. So they remain there. And actually, charge neutrality requires that the twin neutrons should dominate. So you have some, you could have some phi minuses left, some protons, but overall, twin neutrons will dominate at once.
Charge neutrality. So
Charge neutrality of the universe. So QCD hadronization should occur in the charge symmetric way so that you don't produce any net charge number. So for every proton, you have to have a negative state.
very good.
And if you require that, then you would expect that the neutrons should dominate the dark matter. So if you do that, you get away with everything now.
So
You
the
don't form twin
neutron
atoms.
doesn't decay. The neutron doesn't decay.
The neutron doesn't decay because the neutrinos are heavy.
And the neutrinos are heavier than pions, right?
Yes.
What about muons? Muons don't decay.
Muons
So what about, would they over?
But you don't have any symmetry in leptons. So they annihilate away.
That's fine, but the symmetric part, there would be some kind of freeze out, I'm guessing. For muons,
I
and
think
then
so.
they won't decay because the neutrinos are heavy.
Yeah, but they continue annihilating, and they don't dominate their abundance, right?
No, but once after freeze out, if they don't decay, then you would have to.
Yeah, there's a small amount. Yeah.
Then, because it's a symmetric part, not the asymmetric part. Symmetric part is at some point 50% of the even after.
They freeze out.
Yeah,
Okay,
the
they
freeze
freeze out.
the muons would
That-
worry
that-
They probably don't. Yeah,
What is the freeze up temperature?
yeah.
yeah, because the neutrinos are.
No, that's why. So now I'm asking, what
Some
is the freeze
temperature is
up?
probably tens of MeV.
Tens of MeV.
So they continue.
So it will be,
10 MeV, let's say.
Yeah, they continue in the path.
so at that point, they will, a small density will remain. Yeah.
Yeah, I think they should not dominate over protons and over neutrons. We can discuss more.
Okay.
And once we have that, then it's actually interesting because twin nucleon interaction is the ballpark of self interactions for dark matter for bonds like bullet clusters. So you can get some sort of halo-like picture for dark matter. And once you have that, you can do that direct detection experiments. So here are the self-interaction bounds. Sorry, the spin-independent cross-section bounds over the dark matter mass. And this is that narrow region that I said before. And as you go down, you probe larger and larger scales of the vector mediate portal between the standard model and the twin sectors. And this is actually interesting because you have some parameter space above the neutrino fog still to probe by these future experiments. And once you go down the neutrino fog, you can use exposure techniques to probe also a little bit of this region. So should be interesting when you get there. For some scalar.
Sorry, I'm confused. Which one is the neutrino floor for you? The blue?
So now it's a neutrino fog. I think it's a politically correct way to define these days.
Neutrino fog.
Fog, yeah, because you can wait.
Yeah, because it's a background.
Yeah, it's a background. So you can wait enough so that you have statistics, and then you can go down on the neutrino fog.
I see. And how is this neutrino fog computed? Then
This is computed. You can check this.
I have, because I have seen different representations.
Yeah, this I'm using the Snow mass convention. I think this was done by O'Hare and other people. I think as you increase in these curves, you have to increase 10 times the exposure time to get this statistics method.
I see.
Something like that.
Very good.
So you can do something similar to the scalar interaction. For the scalar interaction, we know that there is a Higgs portal. So the Higgs portal is down here, mainly because you get a big suppression for Yukawa couplings. But you see that it's almost entirely down in the neutrino fog. So this should be a little bit harder, but still we can still have some hope around here. This region. Okay, there's another way to do that to reach this 5 relation. We want to have some reason for the number densities being different and this mass range. And the other option is to increase the numbers of twin sectors. So this can be done by looking at this orbifold Higgs picture, which is a generalization of the twin Higgs mechanism. So in the twin Higgs, we have some SU4 symmetry, and we call this an orbifold projection when you have this gauge SU4 theory, and we only keep the fields that respect the Z2 symmetry in the theory. So we orbifold this SU4 to reach SU2, SU2, U1, which is exactly the twin Higgs structure that we had before. And once you realize this, you can generalize it to a gamma dimensional discrete group G in general. So you have, for example, some SU gamma times n, and is a number of colors there. You orbifold project this over G, and then you get some product of SU dn. These are the dimension of the elements of this G representation, and some U1 factors. So, for example, if you do this for a Zn group, then you have some SU n to the n times some U1 factors. So if you choose n equals 6, the Z6 group, then you can orbifold project this group to 6 copies of the standard model and some U1 factors. And this automatically leads to having the number density being 5 times the number density of document. So this is something that I'm doing with Seth. I think it's an interesting, crazy idea, but it's nice to see if we can get away with it.
Amusing.
Yeah. There are some problems that we have to deal with now. The twin neutrinos and the twin photons have to be heavy. Otherwise, there is no way to satisfy the delta effective bounds. We need to annihilate the symmetric parts efficiently because we don't have the twin photons anymore. And we have to deal with these 5 U1 factors. So I'll be happy to discuss this later. But yeah.
A couple of words. So do you make them heavy by the photons by some mechanism, or you just get rid of them by symmetry reasons?
You can always make them heavy by using some Stuckelberg mechanism. But we want to do this in a way that fits, that maybe helps to deal with the annihilation of the symmetric part or something like that. Yeah. So to finish, I would like to just comment a little bit on this last project that I'm doing. It's low temperature baryogenesis and displaced vertices. In the previous model that I showed that realized baryogenesis with this out of equilibrium decays, we needed this sort of diagram for the interference term. And this means and to have a non-zero CPA symmetry, you have to have on-shell intermediate states in this loop. And the syntax is colored. It should be around the TeV scale because of LHC bounds. And this also means that the n should be heavier than x, which is also around the TeV scale. So my question is there a way to realize this low temperature baryogenesis with flight neutral states? Because this doesn't seem to be a really required.
By the way, in the previous mechanism that you told us about, what was the mass of X?
So it has to be like 2 TeV or heavier.
A few TeV.
Yeah, a few TeV.
Mm-hmm. Okay.
And also n, because these guys are on shell, so n has to be heavier than x. So I want to have now a light baryogenesis in neutral sector, and well, let's forget about the twin Higgs distinction. Now I'm talking about something else. The requirements are: first, we need some new states. There are singlets, so I have these n alphas also. Now a neutral scalar. I need also a coupling with a baryon number operator, an operator with baryon numbers. So the easiest, since this operator is a fermionic one, the easiest way to do this is to couple n to O to this operator, and this has to have some 3-quark structure or multiples of 3-quark structure, because the only baryon number in the theory are the quarks. So this leaves also the easiest option is to have n equals to UDT. Since n is a neutral state, you have to choose the flavors here to also be neutral under all, but baryon number. So this is the only option. To have a non-zero CPA symmetry, I will need the 3 flavors of these n's and some Yukawa coupling, as I show you in the next slide. And the requirement of not having proton decay actually fix what is the structure of this operator and what is the UV dynamics in, say, the leptoquark model.
Neutron oscillation.
We don't have that, and I just comment on it. Okay. So the theory is the Lagrangian we need to add now is this one, n coupled to UDD. There is some epsilon contraction for the color indices. And this means that this K will have some anti-symmetric flavor structure in the JK components. Once you go to the UV completion, this is becoming clearer. And you also have this Yukawa coupling.
So dimensionally, 3 fermions in the vertex. So is this, how does it work from dimension point of view? N is another fermion.
N is a Majorana fermion.
Okay. Misunderstood.
So you have a Majorana fermion, then you have this.
Very good, yeah.
N will decay directly
Right,
to 3 part to baryon number. The CP violation will come with the interference with this loop. And this is why we need 3 flavors of N, because one has to be the initial state, one has to be the on-shell intermediate state, and N3 has to be the mixing state. And because of this, we have some non-normalizable operator that decays as a 3-body decay, and the N alphas will be naturally long-lived. Also, phi can be stable if you impose some Z2 symmetry, or it can mix with the Higgs. Either way, it's sort of long-lived. Here is the decay length of N for different couplings. So I go all the way to 1 to 10 minus 8 as a function of the mass of N. And you can see that we can probe several regions of interest. And this can be interesting for displaced vertices surges at the LHC, for example, all the way to beamed up experiments, all the way to the BVN if this is too large. So if you decay very late, then you are decaying below that window that I was saying, and this should be excluded. Now we can plot the baryon symmetry. We'll have some similar expression with depending on the phase and some couplings. Here I'm fixing the phase to P1 just to show you the mass hierarchies that I have in the model. And this is the plot of the mass of N1, which I'm choosing to be roughly the mass of the scalar. It's a function of mass of N2 plotted for different values of N3. So here we have different hierarchies. We can have a very light N1, like a few GeV, and a heavish N2 and N3 around the 100 GeV. You can have some sort of equal hierarchy between them, more or less around here. Or you can also have N1 being a little bit heavier and then N2 and N3 being heavier and close together. So different hierarchy for the masses. And to study this, it's better to include some UV completion. And if you require no proton decay, this can be done easily with a 3-level scalar. This guy, it has a 3. It's in the fundamental representation of QCD, singlet under SU2 and 2/3 hypercharge. And the Lagrangian will be something like this. And as you go to lower energies, you recover that Lagrangian that I showed you before. So this can have very different signals in colliders. For example, we can produce some monojet and some missing energy or a displaced vertice with this N1. You can also, this is also a monojet, but with a different angular distribution. You can have some cascade decays of N2 going to N1. Also, this other XX pair production would lead to something like RPV SUSY searches. You can have 2 jet channels and 4 jet channels, and this can be interesting in several different ways. There's also other phenomenology. Because we are adding 3 Majorana fermions, we can make some connection with neutrinos by coupling these hands to L and the Higgs.
I think you only need 2.
Do I?
Yeah, because one can be massless, one of the neutrinos.
No, sure. Yeah, you only need 2, but since we have 3, you can can use them. And this will be interesting in some sort of low scale seesaw, which is not my favorite model, but it can be done. This phi can be a dark matter candidate. I didn't estimate the abundance, but it can be stable easily. And you have some neutral baryon mixing because you have N1 going through 3 quarks. And if this is light enough, this can mix with directly with hadrons. But because of the flavor structure here, you cannot have 2 Ds. You can only have UDS, for example. So the resonances it mixes to are the lightest one is lambda 0, and then we can go for heavier ones. So yeah, we are still doing this project, but I'm happy to discuss it, and stay tuned for when we release the paper. Okay, this is my summary. I would like to remember the twin Higgs as a sandbox for connecting different problems in physics. It's very interesting in that respect. We can postulate that there is some baryogenesis model and use the Z and T2 symmetry to copy it to the dark matter genesis model. One prediction of this is that we have direct detection at 1 GeV mass range and asymmetric dark matter. And these low temperature baryogenesis models can be associated with displaced and long-lived particles in colliders and beam dump experiments and so on. Yeah, thank you. And it would be very nice if we start to predict and discover new particles in the future again.
Thank you, Pedro. Any questions?
That is a beautiful picture, right?
Yeah, I love it. Sorry.
So this baryogenesis scenario that you proposed in the previous one with the leptoquark, yeah. What sets the scale of the n the n masses?
This is more or less.
You can
Yeah, this is more or less free.
that is free. No, it's not.
The only thing that is constraining it is to reproduce the baryon asymmetry, which is why I made this plot. But you can also, so this is for fixed entry, but you can have very, very heavy entries, and then you can get some more heavy baryogenesis model too.
And the same is true for the other mechanisms that you.
The other one, no, because they have to be heavy because X is colored. So N has to be colored. So they are TVs, the other mechanism.
Well, but n can be even larger, so can
Yes.
be.
Oh no, actually, the one problem is that you have to worry about sphelerons if it's too heavy. Then you can generate B minus L, but here we are only generating baryon number.
Yes, and that is a problem because
Because the sphelerons will wash out anything that's not a B minus L.
but baryon number is not B minus L. I mean, baryon number is B minus L,
Wash out baryon number, yes.
but converts into I mean,
You can, sure, it can be converted to leptons.
B minus L. The net B minus L is always non-zero, right?
Yeah, yeah.
Then will not be washed out. Will be converted to L partially, I guess.
Partially.
Like the leptogenesis is converted to baryons here.
Yeah. Something like that.
Yeah, we'll wash out some.
Wash out half, say half of
Half of it.
it.
Yeah, I was saying that apart from direct